Section 23.8 Heteronuclear diatomic molecules. This is the molecular orbital diagram of hydrogen fluoride. The 1s orbital of hydrogen, the 2pz orbital of fluorine, may interfere with each other in a constructive manner or in a destructive manner. So over here, you have this constructive interference between this plus and this plus. It's a bonding orbital. Over here, you see a destructive interference between this plus and this minus lobe of the 2pz orbital. So there's a nodal plane between hydrogen and fluorine right here. This is anti-bonding orbital. Do not assign G or U to heteronuclear diatomic molecules because there's no center of symmetry. There's no inversion center. There's no symmetric or anti-symmetric symmetry. So there's no G or U. This is a more complete MO diagram. The 1s orbital of hydrogen can also interact with the 2s orbital of fluorine. However, these two atomic orbitals, the 1s of hydrogen, lies so much higher than the 2s of fluorine. The interaction is minimal. In quantum mechanics, you will learn this. If the energy difference between two AOs is significant, they do not interact with each other, even if their symmetry match. So in this case, they do not really interact with each other. Or I want to say maybe there is a very small, negligible interaction. So this interaction can bump this down a little bit, and then bump this 3 sigma up a little bit. So you may wonder, what is 1 sigma? 1 sigma is simply the 1s orbital of fluorine. Can the 1s orbital of fluorine interact with the 1s orbital of hydrogen? Well, yes, if you look at their symmetry. Yes, but the interaction is, I would say it's zero, okay, because the energy difference between the 1s orbital of hydrogen and the 1s orbital of fluorine is huge. Now look at this. We call this pi orbitals, but really they are just the p orbitals of the fluorine atoms. It's just when we talk about the atomic orbitals, we say these two are p orbitals. Now in HF, we call them pi orbitals because they have the pi symmetry. Now let's look at the naming again. If we are looking at a homonuclear diatomic molecule with a D infinity H point group, we apply G and U to denote the symmetry of the MO. So it's 1 sigma G, 1 sigma U star, 2 sigma G, 2 sigma U star. All right? And then 1 pi U, 3 sigma G, these two are bonding, and then 1 pi G star, 3 sigma U star. So this is the order for B2, C2, N2. What if you have O2 and F2? You just swap this two. When you have O2 and N2, there's not much sp mixing, so you put electrons in 3 sigma G before 1 pi U. What about heteronuclear diatomic molecules with a C infinity V point group? Well, first, drop the GU subscripts. So it's 1 sigma, 2 sigma, and then 3 sigma, 4 sigma. This is the first pi. This is the second pi. And then over here, 5 sigma, 6 sigma. All right, so if you are looking at hydrogen fluoride, there are a total of 10 electrons. So 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here, and then 2 electrons here in the hydrogen fluoride, with a total of 10 valence electrons. Sorry, I made a mistake. So in the HF case, this 4 sigma lies above 1 pi. So the order is this: 2 electrons, 2 electrons, 2 electrons, and then 4 electrons here. These 4 electrons are the px electrons and py electrons in the fluorine atom. All right. Yeah, and this is the one of the anti-bonding MO. Now let's look at lithium-2. It's an easy case. This is the electron configuration for lithium-2. What if you have a heteronuclear lithium hydride? Then you have to drop the GU symmetry and then just say 1 sigma 2, 2 sigma 2, and that's it. There are only 4 valence electrons. Oh, I'm sorry, there are only 4 electrons. Okay, 1, 2, 3, 4. And by the way, this 1 sigma is essentially the 1s orbital of lithium. This 2 sigma is the 2s orbital of lithium interacts with the 1s orbital of hydrogen in a constructive manner.